Okay, so we need to talk about dimensions. I've been using this word a lot, so let's actually define it. So, in order to talk about dimension, I need to talk about a thing called a basis. Let me say that I'm going to define the word basis. And then I'm going to go over here a little bit. We'll do some examples before we define the word basis. So, let's consider a space near and dear. Let's talk about R3. Just for a hot minute. You guys good with this? Okay. So, I want to talk about kind of, well, I want to talk about independent sets and spanning sets. So let me talk about linearly independent sets. Oops. So I just want some examples of linearly independent sets of vectors in R3. You guys give me a couple? What do you mean the identity matrix? Okay, so the columns of the identity matrix. Okay, cool. Right, that's a linearly independent set. How do I know?
Whoops.
If you add them together with scalars and get this zero vector, it should be pretty obvious that the scalars all have to be zero, right?
Yep.
That was actually one we did a long time ago. So that's a linearly independent set. I suspect that this is kind of the right size, right? If I'm playing a game of Goldilocks here, I think that R3 and these three things probably have a pretty intrinsic relationship. You guys with me on that? Why do I think that? Well, look man, these are I, J, and K, and I've used the word basis to describe those before. You guys with me on that? I said that though, like, I could be full of shit. I have said things that were wrong in the past, right? So like, that's a linearly independent set. Are all linearly independent sets in R3 inclusive of three vectors? Like, do they all have three vectors, or can you make a linearly independent set with fewer or more?
I think they're all probably fewer.
So, tell me about this set. Right, the vectors I and j are linearly independent.
But in R3 we'd have a row and zeros.
Yeah, so I'm just talking about a set of vectors, right? So, this set of vectors feels too small for R3. You guys see that? Oops, that is not the symbol I want. How about the vector, or the set of vectors just I? Is that also linearly independent? Yeah, right? Okay, so can I make one with no vectors in it? Okay, we'll come back to that in a minute.
The zero set?
No.
Empty set?
Yeah, we'll come back to it. Keep that whole thought, keep it in mind. So, I can have a linearly independent set with 1, 2, or 3 vectors in it for sure. Can I have a linearly independent set of vectors in R3 that has 4 vectors in it?
No, because one of them parameterized a variable.
Say that again?
So, if
Like, can I add a vector to the end
yeah,
of
if there
this?
was a fourth column, then one of them would have to be parameterized by like
other words, not all zero, you mean?
Yeah, like, so if I'm just kind of snowball or spitballing here, like, what if I took that set and I'm like, okay, so I, J, K, and I don't know, like 1, 2, 3.
Sick.
I mean, that'd be independent.
No, that's
Yeah, that is dependent.
Why is this dependent?
Because it's 1I plus 2j plus 3k.
Good.
No.
You guys see that? I can make the fourth vector out of a couple of these. What if I put different numbers in here? So what if I was like x1, x2, and x3?
So yeah, it's still the same thing, it's just x1, x2.
Yeah, I could make a linear combination that got me 0 by doing minus x1i minus x2j minus x3k plus this other vector,
Yeah.
maybe x, right, is going to give me the 0 vector. Okay, so that's, I should be a little bit careful, because if x1, x2, and x3 are all 0, right, if I added the 0 vector here, remember any set with a 0 vector in it is automatically linearly dependent. So either these aren't all 0, in which case this combination gives you the 0 vector, it shows that they're linearly dependent, or they are all 0, in which case it's automatically linearly dependent. You guys see that? So this thing, you can't have 4 linearly independent vectors in R3. You guys see that? Okay, that makes me think that maybe linear independence is something I should be thinking about. But it's clearly not enough because these guys are linearly independent. You guys see that? So in Goldilocks speak, I'm kind of thinking, I'm going to try to make a basis just right. So this is going to be my kind of just right set. Right? Over here, linear independent sets can sometimes be too small. You guys see that? So if I'm trying to make just right, and I've got something too small on the one hand, can you guys tell me what might be too big?
More,
So keep in mind, we're only talking about R3 right now.
more vectors.
Good. More vectors. Ooh. So why is it that these don't feel like they're enough for R3? You guys were hitting on this a little bit earlier. So why don't these feel like they're enough?
There's a row full of zeros.
Where is there a row full of
Yeah.
zeros?
We talked about this like a couple of weeks ago before the mention. You have to like squish or stretch, like do some kind of projection in order to like fill in the information that I'm missing, but like, I don't know where you get it from.
Yeah, you guys are kind of embedding these into something. What is it that you're embedding them into? What are you thinking? Like, I'm kind of actually with you, I just want you to say it. Yeah, so we're thinking about R3 as a vector space, right? And we're looking at these guys and we're saying, these aren't really big enough. Like, what do I mean they're not big enough? What if you, like, what if you span them? You guys are thinking about these as the columns of a matrix, right?
Yes.
And then you're like, well, obviously there's a problem because there's not enough columns, right? You see that?
Yeah.
So let's, instead of thinking about them as columns, well, actually, exactly, let's think about them as columns, but let's do it precisely. Let's think about them as the column space, right? So if I want to think about them as the column space of a matrix, I'm just going to span them. I'm going to say, okay, so I want to talk about spanning sets. So I want you to give me an example of a set of vectors that spans all of R3.
What would be the first one?
So the top one is certainly one, right? Let me just write this as, oh, what the hell, I'm gonna flip it. We'll give you guys a chance to think of another spanning set.
Any scalar multiple times that set right there.
Yeah, you can whack this thing with various scalars. That'll, like, multiples of I, J, and K will still be a spanning set.
Isn't that the point of span though?
Yeah, so what I'm saying by a spanning set is that the span of this set of vectors is R3. You guys see that?
Oh, another one for B.
So, sets S with span of S is R3.
The next one would be the zero matrix.
Okay, let's think about that one. So, if I like span the zero vector, right? What do I get when I span the zero vector? I only get 0, right? You guys see that? So the span of this thing doesn't cover R3. You guys see that? It's not big enough. So this is not a spanning set. So come up with another set that spans R3. Or I will. Here's one. You guys with me? You see that spans? It certainly spans because I, J, and K span the set alone. Okay? And then I have this extra vector in there. You guys see that? So a basis of a vector space V is a set of vectors V1 through Vn I'm going to call this B, right? Calling it B for basis, with span of B is V, and B is linearly independent. You guys with me on that? So, this one, appearing in both lists, is a basis for R3. You guys see that? Is that the only basis for R3? Up here it is. You guys see that? Of the sets of vectors I've written down up here, that is the only one that is both linearly independent and spanning. Let me convince you that that's not the only way to skin this particular cat. So, I need something that's linearly independent and spanning, right? So, here's a set. Let me maybe back up to how I'm constructing this in my head. In my head, I'm looking for a matrix that has 3 pivots when it's reduced. You guys see that? I don't want it to be the identity matrix. So I'm looking for a 3 by 3 matrix of full rank, right? So the easiest way for me to do that is to specify the pivots as something. And the way I'm going to do that is I'm just going to make an upper triangular matrix in my head, and then I'm going to drop it right here. You see that? So say 7, 0, 0 has, as my first column, has a pivot of 7. Second column could be 13, 11, 0. Okay, so now I've got a pivot of 11 in the second row. And third one, I don't know, -8, 46, and -23. Right, so now I've got a matrix with 3 non-zero pivots. So I know these are linearly independent. You guys see that? Or I could sort it out with columns, right? Or constants, rather. See that? Like, I know that if I'm going to add a linear combination, a1 times this first thing, plus a2 times the second, plus a3 times the third, and get 0, that's going to tell me that -23 a3 has to be 0. That'll tell me a3 has to be 0. That's going to tell me that 11 a2 has to be 0. So a2 has to be 0. That's going to tell me that 7 a1 has to be 0. Great, cool. You guys know how that works? Okay, so my claim is this is a linearly independent set. My claim is also that this is a spanning set. How do I know this is a spanning set? I want to know that I can make any vector in R3 by writing some combination of these. That's going to amount, so I know that's going to be a spanning set because solving that equation is going to amount to augmenting a matrix 7, 13, -8, 0, 11, 46, and 0, 0, -23. I'm going to augment that by whatever, right? X, Y, and Z.
You can do that.
And I know that this is solvable because 1, 2, 3 non-zero pivots,
It's fair.
right? Because I made this thing that way. So this shit is also a basis for R3. You see that? Could I add a fourth vector?
No.
Why not?
Because of,
Because it would break linear independence. How do I know it would break linear independence?
Because then you could find a set of scalars where you can add all
because
the
one of the fucking variables would depend on another one. Like, that's what I'm trying to say this whole time.
Okay, so gotta be a bit careful with this because I think you're probably in your head using the concept of dimension. So what dimension is R3?
3.
R3 is 3-dimensional. How many things are in my basis? 3. Do you think that's a coincidence? No. That's the definition of dimension. Okay? So the definition of dimension is literally just the number of vectors in a basis. Now we do need to write down a little quick proof that that's well defined. You guys with me on that? So vector space V is said to be dimension n if any basis for V must have, actually, let me just say has, n vectors. Now, the any part of this is kind of jacking with me, right? We do need to spend a second and show that a basis is always going to have the same number of vectors in it. You guys see that? Cause otherwise, if I could say find a linearly independent and spanning set for R3 that had 2 vectors in it, then I wouldn't know whether R3 was 3-dimensional or 2-dimensional. So we need to know that basis sets always are the same size. You guys with me on that? Okay, so I'm gonna let you think about that for 5 minutes and then we'll write it down.